So welcome to my first video on heat transfer. This time I'm going to be solving an example, radioactive nuclear rod. In this scenario here, what we have is, of course, a nuclear rod in a fluid that's going to absorb the heat that is being generated, P, inside the rod. And we want to find the temperature field on this rod. So like I want a mathematical function that tells me the temperature here, whatever point I want inside the rod. Okay, that's our goal. Okay, so first step, we need to understand what's going on. So this is an infinite rod, which means that it goes infinitely up and infinitely down, which means we can pretty much ignore the boundary conditions on this face here and this face down here, since it doesn't really have an end. So the temperature and heat, right? Temperature is going to be a function, a T of not Z, because that doesn't interfere with the temperature, and not theta as well, because it is a perfect cylinder. It's symmetric. So if we look from the cylinder from above, so this would be our eyes, kind of, we would see the temperature on the wall here, T wall, and then we would see another temperature here. This is a isothermal line, so the temperature would be the same on this line as well, on this line as well. So like the temperature is the same, is like full rings in which the circumference of these circles would be, the temperature would be constant. So T is only a T of R, and Q is only a Q of R, or we can say that this is Q R E R, right? Okay, so heat only flows from radial direction. Okay, so we defined our symmetries. Now we need to define a control volume. So as I mentioned, this was like, if you see this from above, you're going to see a bunch of rings, sort of lines with the same temperature, circumferences with the same temperature. So it will be fitting to have a control volume that resembles a ring. It behaves similarly to our system, so physically. So we're gonna have this ring with radius r, small radius r, and big radius r plus dr, right? Okay. And we can write our energy balance equation, because we define the symmetries, we have our control volume, and then we can just write the energy balance equation for this control volume. So we have the dt equals dH dt, which is equal to 0, which is equal to the integral of some surface of the heat that is coming, CD for the conduction, CD plus the radiation heat, right? Which would be something like this, dot n ds. So when we have plus whatever is being generated inside, so this is volume P dV. Okay, so there is no radiation going on. It's an opaque, I think this is how you pronounce it in English, opaque solid and fluid interacting. So this is going to be just convection from here to here, and convection conduction on the fluid outside, coupling, right? So we're going to have this integral over here. I'm going to call it 1, and I don't know, I'm going to write it with a different color, make it prettier. So we have the integral 1. What is this equal to, right? So just a reminder, this integral over here is equal to phi CD of R, right? If Q is a function of R. Therefore, this integral over here would be phi CD of R times the surface, which is 2 pi R dz, right? Minus, because this is the heat coming in, right? And the heat coming out would be R CD R plus dr of 2 pi R plus dr dz. Okay, is that correct? Let me check. Yes, that's correct. And we're only looking at this term right now, so this is it. And what we can do now is do a Taylor expansion, Taylor development, better development, we can find that phi, or I'm no longer gonna write CD on the top because inside the rod it's only conduction, so it's redundant. Whatever. It's I don't know. I forgot how to pronounce that word. It's not useful. It's unnecessary. So we have phi of r plus dr should be equal to phi of r plus phi r dr plus whatever we have there. We don't care, and we're gonna plug this in over here. So we have the phi r 2 pi r dz minus, this is gonna be phi r plus phi prime r dr times 2 pi r plus dr dz. So what we can do here is apply the distribution. Actually, I'm going to put 2 pi dz in evidence here, so it's going to be 2 pi dz that multiplies phi r minus phi r plus phi prime of r dr. So that multiplies r plus dr, right? Yes. So this is gonna be 2 pi dz that multiplies phi r minus, so this is gonna be phi of r times r plus phi of r dr plus phi prime of r, prime of r times r plus phi prime of r dr squared. Okay, this term goes to banana because dr is too small, and dr times dr would be even smaller. I forgot to multiply an r here, and then these two terms cancel out. Wait, because there's a minus multiplying, right? I forgot to mention that there's a minus multiplying. So 2 pi dz that multiplies minus phi r dr plus phi prime r dr. Okay, minus. All right. Okay, good. We can put dr in evidence, right? Let me see here. I think I'm missing something. 1 second. Yes, I made a small mistake here. I forgot to write. Okay, let me erase this. I forgot to write. Here should be dr as well, right? Because it's phi prime dr times this, and this would be, yeah, exactly. So this would be 2 pi dz that multiplies phi r dr plus phi prime r dr. Then we can put dr in evidence, so this would be equal to 2 pi dr dz that multiplies phi r plus phi prime of r. And there's a trick here. This is dr phi of r dr, because this is exactly the product rule, right? So we have this 2 pi dr dz that multiplies dr phi of r dr. Okay, so this is our alpha, right? This is our alpha. Number one, our integral that I that I called 1. Is it gonna load? Yeah. Okay, so then we need to sum this to that other term here, which is the integral of p dv, which would be p multiplying the volume. The volume in this case would be pi times r plus dr squared minus pi r squared, dz, because, well, this is a ring, right? And then we would have this area over here times dz minus the volume inside here, right? To get the total volume of our control surface, right? This should be equal to 0. Now we can work with this term right here. This would be p times pi can go out by it multiplies r plus dr squared minus pi p pi r squared dz. Now this would be p pi r. Sorry. Is it a better way to do this? Hold on, let me. I think the best way to do is just to do it traditionally and expand this. So this would be p pi times minus p, multiplying this, p pi r squared dz. Hopefully I'm not making any mistakes here. Okay, so this one goes out, and then we're gonna have, and this one's too small, so this is just become p pi 2p pi r dr dz, right? And then we have 2 pi dr dz dr phi of r divided by dr plus, sorry, this should be a minus here if I'm not wrong. I think I ate a minus sign somewhere around here. Yes, I did. And here's not plus. Here should be, oh yeah, if I put the minus there, then it becomes a plus. Yes, sure. Minus this, and then plus 2 p pi r dr dz equals 0. So we divide everything by 2 pi r, 2 pi dr dz r. So this just becomes minus 1 over r dr phi of r dr plus a dr dz. So this one goes to kika, this one goes to kika, this one's go to kika. This becomes just p, right? Yes. Okay. You see, so we just basically arrived on the, what is called, the differential local formulation in steady state, which is just the divergence of q plus b equals 0, right? The minus in cylindrical coordinates, of course, qcd plus qr plus b equals 0, right? That's nice. And then we have the boundary conditions of this problem, right? One that says the phi cd when r equals 0, I like to write it like this, r equals 0 should be 0. Right, this is boundary conditions. So this is boundary condition. I'm gonna say number 2 because I already said that integral above was number 1. So we have number 3 here. We have the phi cd when r equals big R, so like at the wall of the rod should be equal to phi cc. This is the conduction heat flux scalar, because this is nonetheless a problem where there's a coupling between conduction and convection because there's a fluid outside here, right? There's convection here and conduction at the walls. So yes, that's where this comes from. When my thing loads, hopefully, yes. Phi cc when r equals, sorry, when r equals r, which implies that, so this comes from Fourier. I don't know how you pronounce Fourier. Maybe it's like this, Fourier. I don't know. Maybe he's French. I think it's Fourier law, which is minus lambda, the gradient of the temperature field when r equals r should be equal to hcc of tr minus tf, and tf stands for temperature of the fluid. And then you just solve this equation with these boundary conditions. I'm not going to solve it here because this is not a partial differential equation video, it's a heat transfer one. And then you solve this, you find that T of R should be minus TF, which is temperature of the fluid, should be equal to PR over 2HCC minus P over 4 lambda multiplies I squared minus R squared. All right, and that's the solution for this example. So this example is good to understand the steps to solve problems in heat transfer. So first we defined our symmetries, then we saw the dependencies of what temperature depends on what which parameters, theta, r, z, etc. Then we adopted conventions for where the flux is positive, negative, the area vector where is it pointing out, and then we wrote down the energy balance equations. We did some mathematical manipulations here to arrive at the energy balance and the local version of it in steady state. I don't know if I mentioned, but this problem is in steady state. And then with that formulation, we just applied the boundary conditions and substituted into our energy balance, and we found the temperature field on the rod, on any point of the rod. All right, that's about it. Thank you.